All right, let's continue our discussion of Boolean algebra. Not a whole lot new. So this is going to be like finally some new stuff, but it's still very similar, right? It's still very similar to our logic pieces. So yeah, let's continue here. Some new terms. Let's talk about functional completeness. All right, we say that a set of operations in Boolean algebra is functionally complete if any Boolean function that you want to make, so like think of any truth table you ever want to make, think of any combination of ones and zeros on the right side. If you can make this, whatever you wanted, out of those pieces, then those pieces are called functionally complete. All right. So in math, more precisely, it's like a set of operations is functionally complete if a Boolean function can be expressed using only operations from that set. And so, actually, addition, multiplication, and complement, so and or not, are functionally complete. So that's pretty nice. And so they can express any Boolean expression, any Boolean function, anything that we care about writing on the right-hand side of a truth table. So that's pretty cool. So that means that all these other logical symbols, other than and or not, like implication, that can be expressed, right, in terms of some of these. And we learned that. P implies Q is the same as not P or Q. See that? So you can always bring it back to those because these three things together are functionally complete. You can use them to make any truth table. And that we actually learned that. It's just a bunch of, it's like a DNF thing that we can make to build things. And so we can go even further than that. That's not the only set of operations that are functionally complete. Here are two new ones. They're called NAND and NOR. So this is their symbols. Here's the NAND, here's the NOR. So NAND is just, its symbol is the up arrow. It's just do the and first and then negate. So that's why it's drawn like this. Do the and first and then you remember that the dot means like do the negation there. So do the and then negate, that's NAND. And then do the or first then negate is NOR. It's drawn like that. Okay, so that's NAND, that's its truth table. That's NOR, that's its truth table. These, if you get used to them, they're actually really, really cool. Okay? Circuit designers love NAND and NOR gates because they are by themselves functionally complete. So NAND, if you just use a bunch of NANDs, go to Logic Gate Costco and buy just bulk NANDs only, then you can build any truth table. You can build any Boolean function. It's really cool. NAND by itself is functionally complete. Same with NOR. So you can build a CPU out of just NAND gates, just NOR gates. It's really, really, really nice. And so you're like, well, how is that even possible? You might wonder, like, how do I make AND? How do I make negation out of just NAND? Just a bunch of NANDs, all right? Well, let me tell you. Here's an example of here's how you can get just not X out of a NAND gate. Well, not X is equivalent to negate X ANDed with itself, because that's like idempotent law or something. And that's equivalent to X NANDed with itself. So you just NAND X with itself, that gives you its negation. So that's proof, right, that you can get any of these other things, any of these other operations that are more familiar to us humans out of the deal. So that's pretty cute. And then NOR is the same idea. You can build anything out of NOR. So you can build and you can build not out of NOR. You really can. Okay? So yeah. So your entire circuit only needs a bunch of NAND gates. And that keeps things nice and cheap because you can build those, just make a factory that only builds NAND gates, and then you're good to go. All right, so that's pretty cool. So that's functional completeness. Next, let's talk about satisfiability. So this is part of your old lab, so you remember it well now, I hope. A Boolean expression, we say it is satisfiable if there is some way to make it true. There's some way to set the variables involved, the input variables, that make that expression evaluate to 1. Okay? So that's the idea. Like you're given some Boolean function on some variables, x, y, and z. That's what we were doing in our lab. It's like, I don't know, it's like x times y plus z bar. And it's like, go and figure out, are there any ways to make this true? It's like, sure, yeah, just make x and y true, and z can be either true or false. Doesn't matter. So you got two options. So two different ways of changing these variables. Okay? So we say that this is a satisfiable Boolean expression. Okay? In general, determining the satisfiability of an arbitrary formula written in CNF, conjunctive normal form, is very, very hard to do. DNF is very easy, because do you see how you can, like, if you say DNF, like, you can read off all the ways that to make it true. It's like, oh, okay, it's true if I just make W true. Then the whole OR, right, makes the whole thing true. So DNF is very easy, but if you have something in CNF, it's like, this needs to be true, or this needs to be true, and this needs to be true, or this needs to be true, and this needs to be true, or this needs to be true. Then it's very complicated. You can't read off like exactly how to make this true and see if it's satisfiable at a glance. So then it becomes very hard, and it's so hard it's called NP complete, if you've heard of that. So that's just a technical computer science term that means it's really, really hard. Let me try to explain it to you. Here's the idea: polynomial time versus non-polynomial time, essentially. So, okay, there are two sets in complexity theory and computer science. You do not have to understand what I'm about to say. I'm just trying to define this term for you so you can understand it when you look it up on Wikipedia later. So there is a class of problems called P, and then there's a class of problems called NP. Okay? So they look like this, and we're not actually sure if they meet in the middle anywhere. But P problems are problems that are solvable in polynomial time. And polynomial time means like they're like big O of just an n, big O of n squared, anything that looks like a polynomial on your variable n. N cubed is fine. And then NP are problems that we don't think are solvable in polynomial time, but they're verifiable in polynomial time. So like if somebody gives you an answer to a problem that is in this class of problems called NP, then you can verify it with a linear algorithm. So like Boolean satisfiability is NP. It's NP complete, because if somebody tells you like this is satisfiable, they can just give you some truth values and you can check those in linear time. Just plug it through the equation. That's a linear process. But it's not known if it's linear to find whether this is satisfiable in the first place. All right? The best algorithms we know right now for figuring out Boolean satisfiability, and the one that you programmed technically for your lab, was a exponential time algorithm. It was to the power of n. Right? So that's very ugly. That's a horrible growth rate. Gets really, really hard to do. Gets intractable for large sizes, large numbers of variables, where n is the number of variables in your formula, because you got to try every different combination of like true and false, two options for every formula, every variable in that formula. Okay, so that's disgusting, and we can't do any better unless p is equal to np. So the idea is we're not sure if there's any overlap here. If there is overlap, then we can then they are equal, which is a weird proof. Don't worry about it right now. But that's the idea of P versus NP. It's a very hard problem, and we think that right now it's probably not going to be anytime soon when we can solve for satisfiability in a generic, general way. It's a very hard problem right now. So yeah, that's Boolean satisfiability, and you can formulate a lot of problems in terms of Boolean satisfiability. This is not just like a thought experiment. It's not just for a math class. So I'm going to show you a cool example using tic-tac-toe on the next slide. So for example, we can encode whether or not somebody won in tic-tac-toe, or equivalently, how do you win in tic-tac-toe, using a satisfiability problem, using a Boolean expression. Okay, it's just a very complicated Boolean expression. So let's encode this question: what ways are there for x to win as a Boolean satisfiability problem? All right. So, all right, what does that mean? What does that even mean? All right, we have to do the following. We need to represent in Boolean algebra. We need to represent. I'm not going to test you on this. This is just a fun idea along these lines. You need to represent what the board looks like, right? When somebody won, when x won, so we need to represent what the board looks like. And we can do this with Boolean variables. What the board looks like when, first of all, the game is over. When the game is over and x won, because that's what we'd like to express. When the game is over and x won. So let's encode this question as a Boolean satisfiability program. I promise it's possible. So notice that if you have a tic-tac-toe board, you can encode like who's where with Boolean variables. Like if it's true, you can say it's an X. If it's false, you can say it was an O. This is like row 1, column 1, row 1, column 2, a new Boolean for row 1, column 3, etc. B21. So you can represent a tic-tac-toe board, first of all, using 9 Boolean variables. So that's a start. You see that? It's technically possible. 3, 3. And then you just want to figure out, like, and this will encode, like, was it an X or was it an O? And then you need to represent all the different ways that the game could be over in X1. Okay? So here's a valid end game. Let's pretend that X always goes first. Like, so if X went first, like, this is a technically possible game where X went like 5 times, and then O went 5 O goes 1 less time, right? Because O went second, and then there's one way for X to win the game. Okay? So like we want to encode all of the ways that X could win. Like, this is one way. But we don't want to encode any ways that are invalid games, because like here's an invalid game of tic-tac-toe. So here's like, it's impossible for this game to have ever happened in a normal game of tic-tac-toe, right? Because let's say that X and Y go the right number of times. But what else? But something like this happens. So X wins and O wins. That's impossible, right? You can't have 2 winners of a tic-tac-toe game for when the game is over. So that's impossible. That should never happen. So we need to encode that fact, and we can use Boolean algebra. I promise it's possible to do this. All right. So this is trying to motivate the idea of, like, if we had a satisfiability solver program like the kind of that you wrote, then we could do some cool stuff. We could figure out like how to win tic-tac-toe and fancier games. So here are the constraints, the Boolean constraints on the desired boards that I care about. What are the ways for X to win? So here's a bunch of constraints on a tic-tac-toe board. So a bunch of constraints on these variables. Okay. So first of all, every square is an X or an O. So for every square in the game board, it's a Boolean expression, technically, square is equal to X or square is equal to O. Okay. So X could be like, you can encode that as true or false, or like 1 or 0, stuff like that. That's possible. You also need to encode that there is one more square filled by X than by O, because we're assuming that X goes first. Without loss of generality, we'll assume that X goes first in our game. Okay, so that's the idea. So we need a way to like count. We need a way to do math on Booleans. We need to be able to count like the number of X's that are in all these Boolean formula variables better add up to exactly 5 at the end of the game, right? And so this is hard to encode, encoding numbers and like addition in terms of and or not, but computers are built using and or not entirely, so it is possible. And then we want to encode the fact that X won and O didn't. Like, we want to exclude this possibility. So we need to make sure that like somebody won and it was like X won this way or X won this way, like X won along the first row, or X won along the second row, or X won along like the columns. We need to encode like all those possibilities. Like, one of those needs to be true, or X won along one of the diagonals. And we also need to encode that O did not win along any of those. It's not true that O won this row. It's not true that O won this row. O can't win anything. Okay? So that's all the kind of stuff we need to express. And then once we have a giant formula, we can feed that in to a Boolean satisfiability solver, a SAT solver. There are ones that exist in real life. There's the most popular one these days is called Z3. It's made by Microsoft. And so here's a web page that has a satisfiability solver. Here's the satisfiability language. It looks like this. And so let us make a Boolean satisfiability program, give it to the SAT solver that solves for all the ways for X to win the tic-tac-toe game. All right. So this is the program. I wrote it over here, and I'm going to type it in here, and I'll zoom in and show it to you. Let me walk you through it. So that might be, I think that's easier to read that way. So here's my Boolean formula. It's very long, and this is in the SAT solver formula. So this is all getting eventually translated into Boolean logic. Okay, 1s and 0s and ands, ors, and nots and things. So this is a program. It's called smtlib2 This is the program that turns into a Boolean algebra expression. Okay, so let me explain the program. So we're going to encode that x is true and o is false. So x is 1 and o is 0. All right. So I'm going to declare a bunch of Boolean variables to this sat solver. This is how you do it. It looks like Racket, actually. It's kind of cute. It is in that Lispy kind of style. And so here's b11, b12, b13. We're going to encode those as integers, because why not? Numbers, you could encode integers as just a bunch of ones and zeros, right, inside of a computer. So we're going to declare them like that. Eventually, they'll make their way into Booleans. So they exist now. And then here's a helper function, because I need to be able to count how many x's were in the game board and how many o's were in the game board. So here's how I do that. I'm going to count how many x's there were that were set. So this ITE in the Boolean satisfiability solver language, again, I'm not going to test you on any of this. It's just a cool example, I think. This stands for if then else. So if this expression is true, then do this one, give back this answer, or otherwise else give back this answer. So if then else. If this is true, result in this, otherwise result in this. So if then else, if b11 is equal to 1, because x is encoded as a 1, then make this a 1. If b12 is a 1, make a 1. If b13 is a 1, make a 1. And we're just adding them together. Because you can do and in a complicated way, but you can do addition, on Boolean variables. It happens. It's possible. You just need to encode how you add things inside of ones and zero land. So that's all possible, and so that's counting the number of x's and giving back an integer, which you can definitely encode as trues and falses, just a bunch of them, like a 32-bit number. And then this is counting a bunch of o's, same idea. Like if it's a 0, 0 encoded o, then give back a 1 for each of these, and you're just adding up all of them, okay? And then here's a helper function to check if somebody won the game. So this is the question, did 1 question mark, and then you give the player as the argument, and it gives back a bool, true or false. So it's like somebody won, this player right here won the game if they won this row. This is winning the first row. If b11 was equal to the player and b12 was equal to the player and b13 was equal to the player. So that's how you encode that they won this row. So you just try all those. Like either they won that one, or like this is a big or of a bunch of things, or they won the second row, or they won the third row if they're all the same. This is like if they won the first column. b11 is equal to b21 is equal to b31. They're all equal to the player. Okay, whatever play was passed along. So that's how somebody wins, if any of these are true, or them all together. And these are the diagonals, 1, 1, 2, 2, 3, 3, and the other way. So that's checking that this player won, the player that you passed. And so again, this is an and of equality checks. It's just a big Boolean expression. It could be converted to a big Boolean expression. And then finally, we can encode our constraints that we cared about, all these ones. Okay, so here's how we do it. Every square is filled by x or o. So let's assert, this is how you encode something and make sure that this is true. Let's assert that the count for x is exactly 5, and the count for o is exactly 4, because that'll add up to 9 total, all of our variables. That'll cover everybody. And then let's make sure that let's also make sure that there is one more square filled by x. So x went first in the game. It's already taken care of. We also need to keep track of that x won. So assert that 1, the number that we're encoding x by, 1. That's true. Assert that that is a true thing. So x won the game. And then also assert that o did not win. All right? Because that is technically possible. You can have this kind of game board. We don't want to allow that. So let's do that. And so that's asserting that it's not true that o won. 0 was o. All right? And then to solve this formula for a satisfying solution for b11, b12, b13, find them all, you say check sat get model. All right, so that's the Boolean satisfiability language. And so if I execute this, it will give me back a model with all my variables set. Here it'll have some extra variables for no good reason, but here are all the other variables that I've set, b12, b13. And this is one way to make it work. All right, it gives me back one way to make it work. If you want every way, you just have to say like, all right, I don't want that way away anymore. Just assume that that was not true. And so it will, the satisfiability solver, is just looking for one good way to make it work, just to prove it to you that it is satisfiable. So it's saying, yes, it is satisfiable. Here is one way to make it work. You can get them all back if you really want it. All right, so let's write out this formula. So this is, here's the first solution that it gave back, and you can ask it for more. You can be like, all right, I'm done with that one. Give me another one. So let's say B12, say that that's 0. It works if that's a 0. So that was O. B1, this is B12. Row 1, column 2 is a 0. Row 1, column 3, make that an X because 1 is an X. Let's see, these are useless. These are helper variables. B32, that's an X. 32 is an X. B21, that is an O. 21, that's an O. B33, that's an X. So that was that one. So remember, I'm doing this kind of encoding. That's what I'm imagining the board looks like. B23 is an O. 23 is an O. And then B11 is an X. All right, how's X going to win? B31 is an O. Ooh, okay, so we must have the diagonal now. And then B2, 2 is an X. So it seems like the first solution that it found to let X win was this way. And so that's what it encoded. It's like, yeah, that's satisfiable. Your formula was satisfiable. It converted it into a Boolean formula. It's like, it's satisfiable. Here's one way to make it work. And so usually people just want to know, was there one way to make it work? But you can ask it again, like, give me another option. Give me another option. And it will show you every way that X could have won tic-tac-toe if you let it run long enough, which is really, really cool. And so it's very, very powerful. You can encode really cool ideas in terms of Boolean expressions. And we have some very, very nice SAT solvers that try and use some tricks to make it a little bit under this. That's like the worst case running time. Try to get a better case out of it. So that's SAT solving. Anything under the sun, even tic-tac-toe, can be encoded in terms of Boolean expressions, and that's what I'm trying to tell you now. Okay? I'm not going to test you on this or Z3 or this language or anything like that. It's just a really, really cool idea that kind of informs you and gets you ready for CSCI 45, because that's going to teach you like how to build a computer out of just Boolean logic. Okay? So with that in mind, let's keep on trucking. I want to talk about some more topics. Let's talk about K-maps. K-map is short for Karnaugh map. It's a person's name, but I'll just say K-maps. It is a graphical way of talking about a Boolean expression, and it lets you simplify it. All right, it helps you simplify it and use fewer logic gates, because that's usually the goal, because the fewer logic gates you use, the fewer logic gates you have to buy. Okay? So instead of a truth table, instead of writing out like a truth table for the formula you're trying to simplify, because we know how to go from that, right, to values like 0, 0, 0, 1, etc. Instead of doing that, what you do is you turn your expression into not a truth table, but a truth rectangle. For 3 variables, it looks kind of like this. And then you find patterns in this rectangle. It's really weird to think about, right? What you do is you circle groups of 1s where the groups of 1s are of size power of 2. It's either a group of 1, 1, 2 1s, 4 1s, or 8 1s. That's what you start circling, okay? They must be, as well, these groups of those sizes, of those power of 2 sizes, must be rectangles or squares on this diagram. They must not be looking like Tetris pieces. Like, this is not a valid group of 4 things. You can't circle it like this. It has to be squares, rectangles. Cannot look like this. Can't be the T piece in Tetris, okay? So it's a little weird. This square, by the way, does not use the normal looking order. So this is like, this is when A is false, B is false, C is false. This is when A is false, B is true, and C is false. This is what that one is. So it does not look like the normal order of a truth table. The trick for this K-map, for the reason Karnaugh maps work, is that each adjacent cell, they differ by 1 bit. So like these two differ because B got flipped. These two differ because C is getting flipped. See how that's the difference? So let's have an example rectangle. Here's like 1, 0, 1, 1, 1, 1, 1, 1. So this involves 3 variables, A, B, and C. And like this is saying it's a 1 here when A is true, B is true, and C is false. Put a 1 there. So that's how you're filling in your truth rectangle, your K-map. All right? And it's like saying there's a 1 here when A is true, B is false, and C is true. Okay? So that's how you fill it in. And now you go searching for the biggest rectangles you can find. All right? So here's, you want to draw the fewest number of rectangles you can, too. So let's see. I think no matter what, you're forced to draw 3 rectangles here. So like you could draw it this way. Here's one rectangle of 4, right? You're looking for powers of 2. Here's one rectangle of 2, and here's a rectangle of 1. You could do it that way, or you could also do it this way. Here's a rectangle of 4. So I think you're forced to draw 3 rectangles no matter what for this one, just to cover all the ones. So you draw that one and this one, and then just this one all alone. So sad. So that's how you fill in the K-map, and then I'll show you like how this simplifies things. Okay? So here's a bigger example. Let's use a K-map to fill in the truth values for the following expression. All this stuff involving the variables a, b, and c. All right? So, and then we're going to use it to write a simplified version of the expression. I'm going to teach you how to do that on this slide. Okay? So let's fill it in. Apparently this is in DNF. This is very nice. So it's saying that it's true when A is false, B is true, and C is false. So you just find that row. So A is false, B is true, and C is false. So that's this one. So right here we're going to put a 1. See that? So it's saying put a 1 there. That's where you fill it in. And this one is true that you put a 1 again when A is true, B is false, and C is false. A is true, B is false, and C is false. So that lines up right here. So you're going to put a 1 there. And then this is A true, B false, C true. So C is true, where is A true, and where is B false? So there's this one. So there's this one right here. We're going to put a 1. And then finally, A true, B true, C false. A true, B true, C false, right there. Put in a 1. All right? And then everything else, that's like, it's a 0 everywhere else. That's the only ways to make a 1. This is the truth table, the truth rectangle, the Carnot map, okay? The K-map for short. And now what you do is you draw rectangles of power of 2 size, can't be Tetris pieces, and you want to draw the fewest numbers possible. So again, this is not possible, even though it's of size 4, it looks like a Tetris piece. It's got to be a rectangle only. Okay, so here's one, and then here's another, I would say. So here's me circling 2 groups of 2. Those are both valid groups in a K-map. And so here, now let me show you how to take this, and we're going to simplify this into something much shorter. All right, into something equivalent that's shorter. So what you do, the way that you use a K-map is you look for, you take each of your rectangles and you look for what was the same across them. Look for what is the same in each group. Okay, that's what you do. And so like we take this group, what's going on in it? You got A false, B false, C false. You got A true, B true, C false. So what's going on in that's similar about both of these lines? So you underline what's similar. So the A's, those are differing. The A's are different across this rectangle, so that's not helpful. But look at how the B's are both true. The B's are both true for this rectangle. And also, the C is false for this rectangle. And so that, the things that are in common, uniquely specify that rectangle. So you say, all right, this rectangle is, another way to write it is you say that, all right, it is the one where B is true and C is false. So that right here, this just writing only those 2 things exactly specifies that rectangle. Okay, that's the only way, and A can be true or false, it doesn't matter. This is what it means to be that rectangle. Okay, that's the secret. Does that make sense? That's what you look for. All right, and then you OR that with whatever other thing made this true. All right, so now we look at this one. What's true about this one? Well, C differs, so C is not helpful. C could be anything, but always when we're in this rectangle, A is true and B is false. You see that? And so that uniquely describes this rectangle. A is true and B is false. So either we were in this rectangle or we're in this rectangle. We want to one in either case. There's your simplified expression. That's how you use a K-map. Okay? So that's the trick. So hopefully that made a little bit of sense. I'm going to force you to try now. So use a K-map, please, to fill in the truth tables for this guy. Here is the K-map. Dun, dun, dun. Here's what it looks like. So go ahead and fill that in, and we'll try it out, okay? And then try to simplify it, too, using this idea. Try to circle those groups of powers of 2 and simplify it. Okay, so what do we got here? How do I want to do this? let me try and walk you through like why this is all like why this works out, why you write it like this. It's like every adjacent slot going a different way in a different direction means that one bit has flipped, and only one bit has flipped. So this is like C bar, this is C, and this is like A bar, B bar, A is false, B is false, and then this is A bar, B, so B got flipped, and then this is A, B bar, so A got flipped, and then A, B bar, so B got flipped. That's how you do it. So that's your K-map. And now we'll fill it in. So we got, all right, what's true where? Let's figure this out. All right, for here, is A true and A false? I don't think A is ever going to be true and false at the same time. So like we can skip this one, I think, so you can simplify it, right? And then also, same with this one, right? The C true, C false. Like C will never be both true and false. It's impossible to be in a row and have C true and false at the same time. So that's kind of useless. So you might think like, you might look at this and be like, all right, just in my head, right? I might believe that the best, it might lead you to like, before you do the K-map, you might think, therefore, that the best answer, the most simplified form is B, therefore the other things that actually make sense, BA plus BA bar. You might think that's the best answer. But if you do the K-map, I'll show you that's not actually. So, all right, BA bar, that is, just BA, excuse me, just BA. So that's A is true and B is true. Put a 1 there, regardless of what C is. So both of these are going to have a 1 right there. Okay, so you got a 1 here and a 1 here. That's how you read that one. That's what this that's the truth values that contributes to. And this is B true, A false. That's this one. B true, A false, and doesn't matter what C is. So both of these right here get a 1 as well. Everything else, these two contribute nothing because they're useless. Everything else is zeros. And now when you go looking for drawing squares, you can do this. Do you see? One big square of 4. That's a power of 2. That's beautiful. And now, can we write a better simplified version of this expression? What is true about all of these ones? C differs. C is not useful. A differs. A is not useful. What is true across all of these ones is that B is true. And that uniquely specifies that rectangle. B is the final simplified expression. Isn't that cute? So you might think like, oh yeah, it simplifies to this. But no, it actually simplifies to just B. And do you see how the K-map just makes it clear? Just like you look for the stuff in common. The C wasn't helpful for this rectangle. The A wasn't helpful for this rectangle. What is true? What do they all have in common? They have that B is true. And so that describes the rectangle. That's what it means to be that rectangle. It means B is the answer for those ones. Isn't that so fun? So that's going to save you a whole lot of money on your circuitry. You don't even just need a wire. Don't even need any logic gates now. So that's fun. And so like I said when I was talking about SAT solvers, I'm trying to teach you that you can build a computer out of this. Eventually you're going to learn in CSCI 45 that this all works out, right? So like, why do we have these slides at all? Like, what is this giving you in addition to the logic slides? So what's the point of circuits and all that? So the secret answer is that our computers are nothing but giant circuits. All you need are logic gates and then a clock signal that goes high and low, and you can build a computer. That's legitimately all you need. So let me teach you that you can do real computer computation stuff out of logic gates, just like this SAT solver was doing tic-tac-toe somehow, was doing addition somehow out of Boolean expressions, because at the end of the day, it's a bunch of Boolean expressions. How do you make that computer, right? So here's one thing. Let me teach you. For example, on the right is one way that you can use a circuit to add binary numbers, all right? Because what is a binary number but a bunch of ones and zeros? So like if you want to add these numbers, do you know how binary addition works, right? Like here, you add this number to this number, 0, 1, 0, 1, 1, something like that. So let's say we add these. How does this work? Well, you just add these 2 bits, right? and then the answer is a 1. Then you add these 2 bits, and then the answer is a 0, and then you carry, right? Then you add these 2 bits, the answer is a 0, and you carry, because it's Boolean addition. 1 plus 1 is 2, which is 1, 0. That's 2, carry the 1, 1, 0, and this is finally 1, 0 at the end. Look at how this 0 and 1 added together to be a 1. That's really exclusive OR, all right? On the right, this is a circuit that does addition on a single bit of numbers, A and B. So it's like you took in the 0 and the 1. The exclusive OR, this is the exclusive OR gate, by the way. You draw the OR gate and you put another slash. The exclusive OR gate does 1-bit addition. Does it not? This does 1-bit addition. Addition of the A and the B bits, okay? Let me prove that to you, because the exclusive OR legitimately is doing 1-bit addition. A, B, A exclusive OR with B. We've got, again, true, 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 false, right? False, true, false, false, or 1s and 0s. So this is true if they're different, and false otherwise. You see how this is the same as adding numbers, adding 2 bits. This is like, it's adding 2 1s, and it carries the 1, and the answer in that particular bit was a 0, right? You add 2 1s, the result for that bit was a 0. You add a 1 plus a 0, or a 0 plus a 1, the answer is, for that bit, a 1. You see that? Isn't that cute? And then if you add 2 zeros, of course you get 0 as the answer. So that's exclusive OR. It's ridiculous. Not, I guess, what am I trying to say? It's so cool. It's really just doing 1-bit addition, okay? So fancy. So it's really doing 1-bit addition. And then if you need to carry, though, this is called a half adder circuit. There's a full adder circuit that does some things in a different way. But essentially what you're doing is, like, here's your lowest bits, you compute the answer, and then you might have needed to carry, like if it was talking about these 2 bits, like your answer was 0, and then also you need to remember to carry to the next bit. So this is an exclusive OR gate. How do I want to say that? This is exclusive OR gate. This is your AND gate, remember that. And so if you know that you carry if they were both a 1, so you just AND them together, and you know that you needed to carry in that case. Okay, so that's essentially how adding a single bit works. And then what you do is you kind of chain these. You make what are called full adders instead of half adders, but you have a 1 here if you need to carry. Okay, so 1 if we need to carry, and you carry if they were both a 1, right? You carry if they're both a 1, and you put a 0 otherwise. 0 otherwise. So that's that. And so kind of what's happening is, like, let's think about our examples. Let's say that you're adding, like, your first bits were, I don't know, a 1 and a 1. Those are your first 2 bits to add together. And so you feed that to your exclusive OR gate, and, like, the answer is a 0, but you got to carry the 1, right? You feed that into your AND gate, and, like, you're carrying that 1 now. And kind of what you do is you feed that in now to your next. Let's say that your next bits to add in the next place were like 1 and 0. You're going to feed that carry as a new input as well to your sum, so like an exclusive OR 3 things. And then you're also going to see, like, do I carry any of these? So it's like, were these 2 true, or was any other combination of the others true? Like, you're going to feed this in as well into this AND in a weird way. It's like ANDs. You're going to AND them all together maybe, or like OR them. Like, were any of these true? Or 2 of them at all true? And so you'll feed those in, and eventually that computes a fancy carry bit again. So again, like, the sum here is now 1 plus 1 plus 0. So the sum is, again, I guess, maybe 0 in this case, and then you're going to carry that 1, something like that. Okay, so that's kind of what's going on. So that's the secret. That's what happens, and yeah, that's addition circuitry. Okay, you need some extra things after this first one. You need what's called a full adder, because you need to, like, your carry out from the previous bit becomes your carry into the next bit, if that makes sense. Like, your carry out from, this was the carry out from the previous bit, needs to become the carry into the next bit, and then you have 3 digits to add now. So you can legitimately make circuits now to add up numbers, and like that's computation. That leads you to addition. You could do similar things to make multiplication, division, and legitimately a real computer, an entire computer out of all of that. All right, but you'll have to wait till CSCI 45 to fully understand it. So I think that's as much as I want to say. I'm not going to test you on like, well, to make a circuit that multiplies numbers or something. That's more of CSCI 45. But this is just giving you a taste of like, why do we call this something different? This is more about building computers. It really has that in the back of our minds now. So yeah, you're now experts at Boolean algebra. That's all that I wanted to say about these slides. They're pretty short. And so yeah, I think that's everything, and I will see you later.